Today we're solving systems of equations algebraically. We're going to talk about two methods to solve algebraically. The first one today being substitution, and then tomorrow we'll look at another strategy called elimination. These should be review of what you learned last year to solve systems of equations algebraically. Remember, a system is when you're given two equations and you're looking for the point of intersection, if there is a single point of intersection, an XY ordered pair where they meet. So we started off by looking at that graphically, and that is an inefficient method to solve a system, and it's time consuming. So today we're going to look at a better method called substitution. One of the key points today is knowing when substitution is a good method, and obviously how do you use substitution to solve a system of equations. So substitution is when you already have an equation that's solved for a variable. So you already have an equation, like here, we already have an equation that's solved for y. We know what y equals. This is easy to use substitution. This is when you definitely want to use substitution because you know what to substitute. So you can see our first step for solving. If we already have a variable that's solved for x or y, in example 1, it's solved for y, then we'll take that equation and use it in the other equation, substitute what y equals in this example for y in the other equation, and then when we do that, we won't have y in the problem anymore because we're going to take y out and put x minus 5 in its place. So when we do that, we would take the original equation 7x minus 3y equals 11. We're taking y out, and we're using what the second equation tells me y equals, and we're putting that in its place. Obviously, it's a binomial. It's being multiplied by 3, so I'm going to put parentheses around that binomial so that I'm sure that all of what y equals is being multiplied by 3. So when you substitute, your first step will only have one variable left. So you're going to use that equation and solve for that variable. So here we would distribute, combine like terms, subtract on both sides, divide on both sides, and we would figure out what x equals. So now that we know what x equals, we can go back to these original equations and substitute again what x equals to figure out what y equals. Now obviously it would be really easy to plug in -1 for x in this equation that already says y equals. Y equals -1 minus 5. -1 minus 5 is -6. I can also, I don't have to, notice I said substitute the answer into either of the original equations and solve, not both, but I'm going to go ahead and substitute -1 into the first one, because if I do that and I get a different answer than y equals -6, then obviously I've done something wrong. So add 7 to both sides. -3y equals 18, divide by -3, and I'm right back to y equals -6. So that was a good way for me to check to make sure that my x value is the correct x value. I plugged it into both equations and I got the same y value. So now I can say the solution to example 1 is -1, comma, -6. Be sure to write your answer as an ordered pair, and then go and classify that. Remember our classifications from last week. If we have one solution, those are intersecting lines. They intersect at one point. So those are a consistent and independent of one another system. This system is consistent and independent. Now going back to when Is substitution a good option for solving a system? Obviously, not all problems are going to be set up to where one of the two equations is already in y equals or x equals form. However, if you have a variable that has a coefficient of 1, then it would be really easy to get that variable by itself. Or if you have a coefficient that divides into all of the other numbers in the equation evenly, then we would be able to solve for x or y without fractions. So let's look at some of the other examples here. Example 2. A system is given by these equations. Decide the solution. Use substitution. So when you look, we don't know what x equals or what y equals in either one of these equations because they're not in x equals or y equals form. So if that's the case, then we want to get one of the equations in x equals form or y equals form. Well, both of my y values have a coefficient. Y here has a coefficient of 4, 17 and 1. The other numbers are not divisible by 4. My y value here has a coefficient of 8, 2 and 34. The other numbers are not divisible by 8. So solving for y would result in fractions. It's doable, but it's not suggested because let's not work with fractions unless we have to. Here we have x has a coefficient of 1. So obviously x would be the easiest equation to solve for. And if we add 4y to both sides, add 4y to both sides of this equal sign, we get x equals 17 plus 4y, or 4y plus 17. So now we know this equation tells me what x equals. I'm going to use that binomial, 17 plus 4y, and I'm going to replace x in the other equation. So I'm letting one equation tell me what x equals, and then I'm going to substitute that value, 17 plus 4y, into the other equation, hence the substitution method. So let's do that. Remember, I'm plugging something in for x. It is a binomial. I'm going to put it in parentheses because we see that x is being multiplied by negative 2. So all of x gets multiplied by negative 2. Distribute. Combine like terms. 8y minus 8y is 0y. 0y is 0. So the variables cancel out. When the variables cancel out, I'm left with a number statement only. Is this a true number statement? Does negative 34 equal negative 34? Yes. So this will always be a true statement. So that is a clue that it is a special system. No solution would be if this is not a true statement. Infinite solutions would be if this is a true statement. We have a true statement, so the solution would be infinite solutions. All xy ordered pairs are not solutions. Just all of the points on this line are also points on this line. If we were to go back and put both of these in slope-intercept form, we would get the same slope and the same y-intercept, meaning these are coinciding lines. How do I determine that algebraically? I solve using the same strategy I would use any other time, and I see that the variables cancel out, leaving me with numbers only. If the number sentence is a true statement, then that means I'm going to have infinite solutions because they're coinciding lines. If they're coinciding lines, then this is a consistent and dependent system. Okay, example 3. I don't have what x or y equals, but I could easily figure out what this x equals since it has a coefficient of 1. How would I get x by itself? I would subtract 2y on both sides. So negative 5 minus 2y, or negative 2y minus 5. That tells me what to substitute. So I'm going to substitute that for x in the other equation. So I would have negative 7 times all of that. Negative 5 minus 2y. Bring down everything else the same as it is. The only thing I did was take out the x and put what x equals in its place. Solve. 35 minus 14y minus 4y. Simplify by combining like terms. 35 minus 18y equals negative 5. Subtract 35 on both sides. Negative 18y equals negative 40. Oh, I can already see where I made a mistake. Go back up here. Negative times a negative is a positive. 14y. Negative 4y. So this would have been positive 10y. Positive 10y equals negative 40. Divide both sides by 10. So we get y equals negative 4. If y equals negative 4, I'm going to go back and use that in my, really I can use any one of these three equations. Again, if I plug it into all three, I should get the same x value. So if I substitute negative 4 into the one that already says x equals negative 5 minus 2 times negative 4, negative 5 plus 8, x equals 3. Let's do it in this other equation. Negative 7x minus 4 times negative 4 equals negative 5. Negative 7x plus 16 equals negative 5. Minus 16, negative 16, and negative 5 are negative 21. And then divide by negative 7 on both sides, and I still get an x value of 3. So that's just me checking to make sure that this y value does give me the same x value, no matter which equation I substitute. So this has one solution. The solution is 3, negative 4. So this system is consistent and independent because it is intersecting lines. All right, one more example. We're going to solve and classify. Example 4. So here is an example where all of the variables have a coefficient. So you want to look for which variable has a coefficient that would divide into the other numbers. So if I were going to solve for x in this first equation, I would have to add 3y and then divide by negative 12. Well, 3 and negative 7 are not divisible by negative 12, so that's going to give me fractions. Same thing with 3. 12 is divisible by 3, but 7 is not. So I don't want to work with fractions unless I have to. So you can see I highlighted this 2y because if I subtract 8x on both sides, I could then divide by 2, and I would get y equals negative 6 minus 4x. No fractions. Now I know what y equals. I'm going to substitute it for y, and then I will solve the resulting equation. Negative 12x minus 3 times negative 6 minus 4x equals negative 7. Negative 12x plus 18 plus 12x equals negative 7. Here we have opposites on the same side of the equal sign that are going to cancel out, leaving me with a number statement only. This number statement is not true. Not a true number statement. So what does that tell me? It tells me that I have a special system of parallel lines. Therefore, there's no solution. This is an inconsistent system. So in my summary down here where I've given our options, that example 4, I would say no solution. What would I see if I put them both in slope-intercept form? Well, if they're parallel lines, they have the same slope but different y-intercepts. I found that algebraically because when I used the substitution method, the variables canceled out, giving me 0x, no more variable. Therefore, I'm left with a number sentence that is not true. Now try the practice problems in the homework section of your notebook.